Hi everyone, the channel Easy Lecture welcomes you. So in this video we are going to discuss the next 50 formulae which are involved in the electronics and communication engineering paper which I prepared to appear for a competitive examination that involves a technical paper of electronics subject. So here in this part, so already we have completed up to 150 formulas. In this part again we are going to start from 151th formula to 200 formulae. So let us move on. 151. So we are discussing the characteristics of ideal operational amplifier. Here, formula number 151, CMRR for an ideal operational amplifier, common mode rejection ratio, that is equal to infinity. 152, slew rate for an ideal operational amplifier is also infinity. Bandwidth of ideal operational amplifier is also infinity. PSRR equal to 20 log of del Vs divided by del Vi naught, that is equal to 12 dB. Formula number 153, V naught equal to A into V1 minus V2. The output voltage is that directly proportional to the difference between voltages of 2 ohms. 154, slew rate equal to maximum of dV naught divided by dt for U of t. 155, slew rate equal to A suffix Cl dot Vm dot W, that is equal to ACL into Vm into W divided by 10 power 6. Omega is equal to 2 pi f. So omega is the angular frequency, and we have 156 for inverting amplifier, AV is equal to V naught divided by Vi, that is equal to minus RF divided by Ri. So this is voltage gain. For non-inverting amplifier, AV equal to V naught divided by Vi, that is equal to 1 plus RF divided by Ri. Again voltage gain for a non-inverting amplifier. 158, voltage follower, AV equal to V naught divided by Vi equal to 1. For a voltage follower, the output voltage and input voltage, they are same. Output voltage follows the input voltage, so that is why it is called as voltage follower. 159, for adder, V naught divided by RF equal to negative of V1 divided by R1 plus V2 divided by R2. If R1 equal to R2 equal to RF, then V naught equal to negative of V1 plus V2. So here we have got the addition of two voltages. So that is why this circuit is called as adder. For differentiator, V naught equal to minus RC into d by dt of Va, that is equal to, if capacitor is used, we can use this formula. If inductor is used, that becomes minus L divided by R into dV by dt. For integrator, V naught equal to minus 1 by RC into integration of Va dt. So if you use inductor instead of capacitor, the formula becomes minus R divided by L into integration of Va into dt. Formula number 162, for difference amplifier, this is the circuit. So the voltage is given to both inverting pin and non-inverting pin, and V naught, the output voltage is the difference between the voltages of these two pins. V naught equal to VB minus VA. Formula number 163, a logarithmic amplifier. For logarithmic amplifier, the output voltage is equal to minus eta into Vt into natural logarithm of Va divided by Id into R, where Vt is thermal voltage and Va is the input voltage, Id is the diode current. Now for monostable multivibrator, T is equal to 0.69 into R1 into C1. So this is the time period for a monostable multivibrator. For monostable 555 timer, tau equal to R1 into C1. So the time period for 555 timer is R1 into C1. For a stable multivibrator, so monostable multivibrator means there will be only one stable state. Okay, so when the switch is activated, either 0 will be a stable state or 1 will be a stable state. So when switch is activated, the output goes to the unstable state and returns back immediately to the stable state. Okay, so that is monostable multivibrator. So only one stable state. A stable multivibrator means there won't be any stable state. The output here switches back between two states, so it will not be in any stable state. Okay, there won't be any stable state for it. So for example, the output switches between 0 and 1 continuously. It doesn't stay in one state. Okay, so that is a stable multivibrator. And here this stable multivibrator can be used as a square wave generator. Okay, so this is the reason why a stepper multivibrator can be used as a square wave generator. Okay, now 166 T is equal to T1 plus T2, that is equal to 0.69 into R1C1 plus 0.69 into R2C2, that is equal to 0.69 into R1C1 plus R2C2. 167, so the application of this formula, so derivation of, we have applied the condition. If R1 equal to R2 equal to R and C1 equal to C2 equal to C, then T is equal to 1.38 into RC. Okay, just from this formula we have derived it. From 168, F is equal to 1 by T, that is equal to application of this, reciprocal of this, 0.7 divided by RC. Okay, now 169, phase shift provided by a single RC network in an n-stage phase shifter is equal to 180 degree divided by n. Now amplitude modulation, SAM of T is equal to, so amplitude modulated signal, that is equal to AC into 1 plus mu into cos of 2 pi FMT into cos of 2 pi FCT. SAMT, so a derivation of this one. SAM of T is equal to AC into cos 2 pi FCT plus AC into mu into cos 2 pi FMT into cos 2 pi FCT, where FCT is the frequency of carrier signal, FMT is the frequency of message signal. This is equal to AC, and AC is the amplitude of carrier signal, and here we have not considered the amplitude of message signal. AC into cos of 2 pi FCT plus AC into mu divided by 2 into cos 2 pi FC plus FM into T plus AC mu divided by 2 into cos of 2 pi FC minus FM into T. So here we have applied the formula of cos A cos B. Okay, cos A cos B is equal to cos of A plus B plus cos of A minus B, the whole divided by 2. So that is what we have applied here. Bandwidth for an amplitude modulated signal is 2 FM, and the total carrier power is equal to AC square divided by 2R. In upper sideband, the total power is AC square mu square divided by 8R, that is equal to PC into, so application of this one, PC into mu square divided by 4R, no, mu square divided by 4. Then the power in LSB, lower sideband, is equal to AC square into mu square divided by 8R, that is equal to PC into mu square divided by 4. From formula number 177, the total power PT is equal to power of carrier, power in upper sideband plus power in lower sideband, that is equal to AC square divided by 2R into 1 plus mu square divided by 2, that is equal to PC into 1 plus mu square by 2. Okay, so these formulas are highly important, and a lot of questions are asked in competitive examinations related to this formula. Now from this, power in sideband is equal to, so sideband only, so we are rejecting the power of carrier. So power in lower sideband plus power in upper sideband, that is equal to AC square into mu square divided by 4R, that is equal to PC into mu square divided by 2. If mu is equal to 1, so mu is the modulation index. Okay, mu is modulation index. If mu is equal to 1, that means it is 100% modulation. So total power is equal to 3 by 2 of PC. So here in this formula we are applying mu is equal to 1. So when we apply here in this formula, we will be getting the total power as 3 by 2 of carrier power. So that means carrier power equal to 2 by 3 of total power, that means 66.6% of total power. Okay, so power in sideband is remaining percentage, 33.3% of total power. So for an amplitude modulated signal, okay, double sideband full carrier signal, what happens, the carrier is also involved, then upper sideband lower sideband, both the things are involved, and lot of power is concentrated in carrier. Okay, so a lot of signals power is carried by carrier, 66.6%, remaining 33.3% contains the information in sideband. Modulation efficiency gamma eta equal to PSB divided by PT, that is equal to mu square divided by 2 plus mu square. Mu is modulation index again. 181, mu is equal to A max minus A min divided by A max plus A min. 182, so A max means maximum amplitude, A min means minimum amplitude. A max is equal to AC into 1 plus mu, A min is equal to AC into 1 minus mu. AC is equal to A max plus A min divided by 2. Then 185, mu modulation index A equal to AM divided by AC. AM is the modulated signal, the signal which has to be modulated, the signal which contains information. So that amplitude divided by the amplitude of carrier signal. Okay. 186, IT, the total current IT equal to carrier current IC into root of 1 plus mu square by 2. 187, VT, the total voltage VT equal to VC into root of 1 plus mu square by 2. Okay, now multi-tone AM. So multi-tone AM means here we are having lot of message signals instead of a single message signal. So in multi-tone amplitude modulation, what happens? Lot of message signals are carried by a single carrier. Okay, so the message signal m of t is equal to a into m1 into cos of 2 pi fm1t. This is one message signal, plus a m2 into cos of 2 pi fm2t. This is another message signal. So like that it goes on. Okay, and here fm1 is the frequency of message signal 1, fm2 is the frequency of message signal 2. So like that is it goes on. Then SAM of the amplitude modulated signal is equal to AC into 1 plus Ka into mt into cos of 2 pi fct. Okay, SAMT equal to AC into 1 plus Ka into AM1 into cos of 2 pi fm1t plus Ka into AM2 into cos of 2 pi fm2 into t. So here we have considered only two signals instead of these extras. We have considered only two signals and we have proceeded the formula for those two signals. So for considering these two signals only into cos of 2 pi fct. Here Ka into AM1 is the modulation index 191, Ka into AM1 equal to mu1, Ka into AM2 equal to mu2. So substituting this modulation index in this formula we will be getting SAMT equal to AC into 1 plus mu1 into cos of 2 pi fm1t plus mu2 into cos of 2 pi fm2t the whole into cos of 2 pi fct. Formula number 193, bandwidth equal to 2 into highest message signal frequency. Okay, so here when two message signals are there, we have to consider the maximum, the signal having the highest frequency, and we have to multiply it by 2. That gives the total bandwidth. Formula number 194, total power equal to PC into 1 plus mu t square divided by 2. 195, IT equal to root of, IC into root of 1 plus mu t square divided by 2. VT equal to VC into root of 1 plus mu t square divided by 2. 197, efficiency is equal to mu t square divided by 2 plus mu t square. AM demodulation, envelope detector method. So this is a method of detecting amplitude modulated signal. Formula number 198, RLC is equal to RLC should be less than or equal to 1 by 2 pi fm root of 1 minus mu square divided by mu. The double sideband suppressed carrier signal. So double sideband suppressed carrier means this amplitude modulated signal will have upper sideband signal and the signal in lower sideband, whereas the carrier signal is suppressed. Since the carrier signal, it doesn't have a lot of information and it is a redundant while detecting the signal in the receiver end, so it has to be suppressed to improve the efficiency of the entire amplitude modulation system. So that technique is called as double sideband suppressed carrier. Double sideband will be present, carrier will be suppressed. Okay, so here for this one, the signal double sideband modulated signal should be equal to AC into m of t into cos of 2 pi fct, bandwidth equal to 2fm. So bandwidth is 2fm because upper sideband is also present, lower sideband is also present, both the sidebands are present, so bandwidth is 2fm. So with this 200 formula is getting over, so we are completing the 50 in this part we are completing this 50th formula from 151 to 200. So with this we are stopping this part and meet you again in the next part, in which the next 50 formula will be discussed. Until then, bye, thank you.